All right, so sorry. I just realized we weren't recording. I'm not gonna go over everything again. Thankfully, most of that stuff was from before the midterm, so it should be okay. Uh, but yes. Yeah. So then we have this. This is called an indicial equation, and then we get its roots here, and then that is our general solution there. And this is called Euler's differential equation. Right? Then, if we have something in the form y double prime plus p of t y prime plus q of t y, which I'm actually going to write just down below here. Equals 0. Here we have to use our series solutions. Okay. So, in this case, we have that p of t and q of t are both polynomials. Okay. That just makes these computations a lot easier. And then if we have that if we have that the left-hand side is defined when t equals 0, then we can assume that our general solution can be written as a Taylor series centered around 0. So y is equal to the series from n equals 0 of a n t to the n. Okay. And then we have to do a bunch of bogus to get what this sequence actually looks like. Okay. But then if the left-hand side is undefined at that point, we say that there is a singularity at t equals 0. All right. So, in the case where there is an irregular singularity, which means that the limit as t approaches 0 of t times p of t, and the limit as t approaches 0 of q of t times t squared. Okay, if either of these don't exist, or are equal to plus or minus infinity, okay, then we call this an irregular singularity, and we can't do anything with that. All right, we can't assume a solution using a Taylor approximation. But if we have a regular singularity, which, as you can imagine, just means that the limit as t approaches 0 of t p of t, and the limit as t approaches 0 of t squared q of t, they both exist, and they're not infinite. Okay. In this case, then we're able to do a Taylor approximation, but we need to edit it a little bit so that we make sure to account for the singularity here. Right? So we assume y is equal to the series starting at 0 to infinity of an t to the r plus n. Okay. And again, we have to solve some initial equation to get what that r is. Okay. So we solve r times r minus 1 plus p naught. So this is p evaluated at 0 times r plus q naught is equal to 0. Okay. Sorry, it's not evaluated at 0. It's this limit. Sorry. It's this limit here. P naught and Q naught here. Okay. Once we solve this right over here, then we're able to actually compute our series solutions, right? So there are 3 more cases we need to look for. So if R1 minus R2 is not in the integer set, then we say that our general solution is exactly what you'd expect. The series an t to the r1 plus n plus the series from n equals 0 to infinity an t to the r2 plus n. Okay. But then probably the most annoying case is if r1 minus r2 is some integer, right? So if that's the case, then we say that, I'm sorry, I'm just referring back to my notes here. Yeah. We say that y1 is equal to the series from n equals 0 to infinity of t to the n plus r1 an, where r1 is less than r2. Okay. And we say that y2 is equal to it is equal to a ln t times y1 plus the series from n equals 0 of some sequence Cn in terms of R2, okay, times t to the n plus R2, right? And now this constant a is just equal to the limit as r approaches R2 of r minus R2 a capital N of r, okay, where n is equal to r1 minus r2, okay. And the reason why we have this variable here, that of r, is just because our sequence right up above, yeah, our sequence that we get over here is gonna be in terms of just a generalized r when we work with this with this expression here. And we'll see that with an example later on. So yes, we have this constant, and then we have this sequence here. Cn is equal to r minus r2 times the sequence in terms of r, its first derivative evaluated at r equals r2. Okay. So, yeah, that one is pretty complicated, but we're gonna go through a question with that case, I promise. So yes, we have that. Are there any questions with any of this so far? anything at all. Okay, cool. Now, if we have the case that R1 minus R2 are equal to 0. Oh yeah, and of course, I'm sorry, I forgot to mention, y is equal to C1 Y1 plus C2 Y2. Okay, and maybe I shouldn't use C's here. I'll use like alpha 1, alpha 2. Yeah. And just as a reminder, this is Y1, this is Y2. Okay. So if R1 minus R2 is equal to 0, aka we have equal roots, then we have that y1 is equal to the series of an x to the n plus r. I'm going to set r to be equal to r1 to be equal to r2. Okay, n equals 0 to infinity. And then y2 is equal to ln. Wait, I should keep this consistent and have t here. Yeah, ln t y1 plus this series from n equals 0 to infinity of uh of this. Just wait, let me double check. I think I might have a typo in my notes. Just give me one moment really quickly. Do-do-do-do. Let's see, let's see. Yep, yep. Uh-huh. Yeah, okay. I did get it right. Yes. All right, so you're taking the derivative of an in terms of r, okay? And then you evaluate it at r, Yep. Oh, why is that there? Okay, perfect. Yes, you evaluate it at r, and then you multiply this by t to the r. Sorry, t to the n. There we go. Okay, yes, t to the n plus r. All right, cool. So those are those cases. All right. Series solutions questions are in general what people struggle with most in this course. So I'm going to try to place a big focus on that. But yes, that is series solutions right here. Also, don't stress out too much if you miss anything. We're gonna post all these notes. Like we're gonna put them up. So don't worry, it'll all be available to you. But moving on to the very last thing, we have systems of linear ordinary differential equations. Okay. And so for this, you might have a differential equation that looks like x prime is equal to some a11, sorry, a11 x plus a22 y. Or you might have something where y prime is equal to, sorry, this should be a 1, 2, a21x plus a22y. Okay, so this is a system of linear ODEs, which can be expressed like this. So we have x prime, y prime is equal to a11, a12, a21, a22 times x, y, right? And we can label this as just a times some x, some vector x. Okay. In this case, our general solution is simply c1 e to the lambda 1 t v1 plus c2 e to the lambda 2t v2. Okay. And we have that lambda 1 and lambda 2 are eigenvalues of A, and v1 and v2 are their corresponding eigenvectors. Right? So yes, that is the general solution there. And yeah, that should be that. In this case, we still might have the case where the derivative of this vector here is equal to ax bar plus some other vector. So this is called a non-homogeneous system of linear ODEs. Okay. And in this case, you have to go through a pretty similar thing as what we did before, finding out a general solution, then finding out a particular solution, and then adding them together, and then you have that as well. Yeah, I will also be going over an example for this. Okay. A couple of other things. This is just kind of miscellaneous, I guess. There is something called the Wronskian, which is if we have y1 and y2, and their solutions for some differential equation. Okay. Then the Wronskian in terms of y1 prime, y1, y2 prime, y2 is equal to the determinant of y1, yes, y1 prime. Oh, wait. Okay, wait. Let me just double check on my notes. I don't trust my gut. Wronskian. Okay, yeah, my gut was wrong. It's good I double checked. Y1, y1 prime, and then y2 prime here. Okay, so we look at this determinant, and then of course it's equal to this. So now with this Wronskian, we either have that W is equal to 0 for all t in R, or W is not equal to 0 for all t in R. Okay, so you might be given a question where it's like, oh, can these y1 and y2 ever be independent solutions to a differential equation? And then And then if you want to disprove it, you would just show one instance in which it's equal to 0, and then one instance in which it's not equal to 0, and then you're good. Or you might have to prove that it's equal to 0 always, or that it's never equal to 0. Okay. Yes. All right. So that is the very, 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 very long rundown. Are there any questions before we move on to some actual questions? Some problems? Anything at all? Don't be shy. Okay, perfect. All right. Would y'all prefer for me to start with like more easier things, or should I just go straight with the Frobenius? Because I know y'all are busy. I know probably Frobenius is the harder thing you guys are trying to figure out, so I can start off with that. Are there any opinions? Okay, there are no opinions. Cool. Oh, there is an opinion. Frobenius. Yeah, that's what I thought. Okay. So, uh, yes. So for Frobenius, I am going to use the following example. Wait, let me just make sure this is the right one. Yeah, it is. Okay. So, example number 1, Frobenius. So we're going to solve the second order differential equation, x squared y double prime plus x squared minus 2x y prime plus 2y is equal to 0. Okay. So, before we can actually incorporate Frobenius and do everything well, we need to actually double check all of our work and everything, right? Or double check that we can even use Frobenius, right? Because we need to make sure that we have a regular singularity here. So yeah. Okay. So we can simplify this to be y double prime plus x squared minus 2x over x squared y prime plus plus 2y over x squared. Right? Yeah. Is equal to 0. Okay. So we need to take our limit as x approaches 0 of this expression right here multiplied by x. Okay, so we have x times x squared minus 2x divided by x squared. This will, of course, be equal to the limit as x approaches 0 of x squared minus 2x over x. This is equal to the limit as x approaches 0 of x minus 2, okay, which will, of course, just be equal to negative 2, right? So far, so good. This limit exists. Then, if we have the limit as x approaches 0, we need to multiply by x squared, and now we're looking at this variable coefficient right over here. So we have times 2 over x squared. The x squareds cancel out, and we just have that equal to 2. And this will be equal to q naught. All right. So we're good. Therefore, we know that this is a regular singular point. And we can assume that that our y can be written as a series that looks like this: an x to the n plus r. Okay. I'm gonna be right back. I'm very, very, very thirsty. I'm gonna run and get water. Okay. Hello, everyone. I'm back. Okay, so yeah. So now we can assume that that will be our general solution. And before we go any further, we need to find the roots using the initial equation. So we have, oh my gosh. Ah. So we have r times r minus 1 plus r p naught plus q naught is equal to 0. Okay. So that would imply r times r minus 1 uh oh minus 2r plus 2 is equal to 0. I got this minus 2 from this expression right over here, and I got this plus 2 from this expression right over here. Okay. So that implies that r squared minus 3r plus 2 is equal to 0. And then we have that r1 is equal to 2, and r2 is equal to 1. Okay. So this is the time in your final where you groan to yourself because you're like, oh no, there's a difference by an integer. All right. So that means that we're gonna have to use this whole very, very, very long and complicated process here. Okay. But it's okay. We'll get through it. We'll get through it. Again, if you have any questions at any point, just leave them in the chat. So yes. Okay. So firstly, just give me one moment. I see. Okay. Yeah. So we've assumed that yeah, okay. So we've assumed that y is equal to this series over here. N x to the n plus r. Okay. So that means that we can substitute this back into our original equation right over here. Okay. Actually, the one just up above. Yeah. All right. So knowing that, we can write the differential equation as follows. So we have x squared times, oh, so sorry. Another thing is that we know that y prime will be equal to the series from n equals 1 to infinity of an x to the n plus r minus 1 times n plus r. Okay. Then we also know that y double prime will be equal to the series from n equals 2 to infinity of an times n plus r times n plus r minus 1 times x to the n plus r minus 2. Okay. Ay, ay, ay. All right. Yes. So, something in the chat. Can you read it? One question regarding has how do we evaluate U1 in the case that W is equal to 0? Okay. I will take that up right after I finish this. I have a differential equation. Yeah. I have a differential equation that should help out with that question specifically. Um, so yes. Yeah. Don't worry. I will go over that. But yeah, no, sorry. I kind of need to rush through this for obedience because there's so much content. But yeah. Okay. So then we have x squared times this expression right over here, n plus r minus 1 x to the n plus r minus 2. Then we have oh shoot, we're adding this with x squared minus 2x times this series expression for y prime n equals 1 to infinity an x to the n plus r minus 1 times n plus r and then plus plus 2 times the series n equals 0 to infinity an x to the n plus r. And then all of this is equal to 0. Okay. So knowing this, we can generalize our series by multiplying in all of these polynomials here. Okay. So this will then be equal to, or this is equivalent to, the series from n equals 2 to infinity of n plus r times n plus r minus 1 times x to the n plus r plus the series from n equals 1 to infinity of an x to the n plus r plus 1 times n plus r minus the series from n equals 1 to infinity times 2 of an x to the n plus r times n plus r, and then all of that plus the series from n equals 0 to infinity of 2an x to the n plus r. And all of that is going to be equal to 0. Oh, okay. So now we have this very, 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 very long expression. Okay. And we're going to try to come up with a general solution for our ANs. Okay. So this, I'm not going to do all of the work to get this initial an equation, but we can say that an is equal to negative n plus r minus 1 times an minus 1 divided by n plus r times n plus r minus 1 plus n plus r times negative 2 plus 2. Okay. And we get this expression just by manipulating all of these things up above. There's also a formula that you can memorize to just get directly here. But I don't know if it was taught to y'all, so like I don't know if I could show it. But yeah, you just manipulate it here, and then you end up getting this expression right here. Okay, awesome. So we're going to start off by solving what our an expression should be for R1 is equal to, just give me one moment. Yeah, okay. Yeah, our expression for R1 is equal to 2. Okay, so we have an is equal to negative n plus 2 minus 1, an minus 1 divided by n plus 2 times n plus 2 minus 1 plus n plus 2 times negative 2 plus 2. Okay, so now this simplifies to negative n plus 1 an minus 1 divided by n plus 2 times n minus 1 plus 2. Okay, now this is going to simplify to be negative n plus 1 an minus 1 divided by n squared plus n minus 2 plus 2. Okay, so these cancel out. We get negative n plus 1 an minus 1 divided by n times n plus 1. Then these cancel out, and then we just nicely get negative an minus 1 divided by n. Okay. So now, this expression, divided by n, this expression is going to work for all n greater than or equal to 1. Right? But in this course, it's not enough to just have this relationship here. We need to actually establish establish what our recurrence relation is without having any sequence numbers in there. Okay. So if we let a naught be equal to 0, then I'm just double checking that this is right. Wait, is this right? A naught, I believe it's supposed to be a naught is equal to 1. 1 over n. Yeah. Okay, yeah. If we let a naught be equal to 1, then we get that our generalized expression is 1 over n factorial times the big product of k equals 1 to n of negative 1 to the k. Okay. And we can get this very simply by just coming up with iterations of this ourselves. You know, I remember when I was taking this course, the main way that I figured out what to do with these was just writing down what every term should end up being. Okay, so here we'd have negative 1 over 1, and then yeah, and then this would turn into that would be negative 1 over 1 times negative 1 over 1 divided by 2. right? And then we have negative 1 over, sorry, that would be positive now. And we have negative 1 over 2 divided by 3. And then we have 1 over 6, 1 over 6 divided by 4. And then you can start seeing the pattern here that is coming up, right? So then with this, you're able to come up with, oh, what? Oh no, the window closed. Just give me one moment. Okay, sorry about that. I saw a comment. No, it's not all gone. Don't worry. It's all here. Um, yeah. Should it be just negative 1 to the n? Negative 1 to the n. Oh, yeah. That would be a simpler expression than having this here. Yeah. I mean, you could simplify this further to get negative 1. I mean, 1 over n factorial times negative 1 to the n. Yeah. That does work. Thank you for pointing that out. Yeah, let me just write down what we had before. Negative 1 over 2 over 3, 1 over 3 factorial divided by 4, negative 1 over 4 factorial divided by 5. Okay, perfect. So we have that relationship right there. Okay, so now we can define y1 to be equal to this series right here, the series from n equals 0 to infinity of 1 over n factorial times negative 1 to the n times x to the n plus r1, which is, of course, the series from n equals 0 of 1 over n factorial, negative 1 to the n times x to the n plus 2. Okay. So then we have our first solution, but as aforementioned, for our second solution, we're going to have to put in a lot more work. Okay. So we have y2 is equal to y2 is equal to a ln x y1 plus x to the r2 times the series from n equals 0 to infinity of cn evaluated at r2 times x to the n. Okay. So with this, we first want to compute what this a value is. Yes, so yeah. So this a value, okay, when we're looking back at, okay, so our formula for a is just going to be the limit as r approaches r2 of r minus r2 a capital N of r. Okay. Now this function right here, we actually want to look back at Yeah, we actually want to look back at this original expression all the way back up here. Okay, so yeah, you have to go all the way back up. You cannot just take this expression here because this expression isn't in terms of r, right? So you're gonna end up having a very, very, very weird final answer if you use this. Okay, that's a very, very, very common mistake. You have to use this general solution for an. All right. So our capital N in this case is just 2 minus 1, which is equal to 1. It's 2 minus 1 because R1 is 2, R2 is 1. Their difference is just 1, right? So we evaluate the limit as R approaches R2 of R minus R2, A1 of R. Okay. And then we can look back at this expression right over here and just plug in that n equals 1. Okay, so this is equal to the limit as r approaches 1, so this is just r2 of r minus 1 times negative negative 1 plus r minus 1 times a naught, which we know is just 1, so we could just leave that be, divided by 1 plus r, 1 plus r minus 1 plus 1 plus r times negative 2 plus 2. Okay. So this simplifies to just be the limit as r approaches 1 of r minus 1 negative r divided by r plus r squared minus 2 minus 2r plus 2. Okay. And this is equal to the limit as r approaches 1 of r minus 1 negative r divided by r squared minus r, which is equal to the limit as r approaches 1 of r minus 1 times negative 1 over r minus 1, which is just negative 1. Okay, are there any questions to do with how to compute that constant a? Again, the most common mistakes are just not using your correct expression for an here, right over here. You always, always, always need to make sure that you're using the expression that is in terms of r generally. Okay? All right. Okay. Cool. Yes. So now we can move on to our expression for Cn. So we have Cn. Just give me one moment. I'm looking through my notes again. Yeah. So our general equation for Cn is r minus r2, sorry, r minus r2 times an in terms of r. Okay, all of this prime, so we're taking the derivative of this, and then we have to evaluate, sorry. Yeah, wait. Yes. Yeah, and then we have to evaluate this at r equals r2. Okay, so yet again, what most people miss out on is using this general equation here for an of r. Okay. And make sure not to just substitute in R2 right away. Which I know sounds like a silly mistake, but it's a mistake I did when I was taking this course a few times. Um, where you substitute R2 too early, and then you just get that your derivative is equal to 0, and then your solution is just automatically wrong. Um, so yeah, make sure not to do that. So we can write down that Cn is equal to R minus 1 an of R all of this prime, and we have a general solution for an of R. Okay, so yeah, just give me one moment. Over yeah, okay, yes. So this will be equal to R minus 1 times negative. I'm sorry, you can tell there are a lot of moving parts in these questions. Um, negative n plus R minus 1 an minus 1 uh minus sorry. Oh wait, what? I've just confused myself so much. Just give me one moment. Yeah, and and then okay. Yes. Okay. An minus 1, then all of this divided by n plus r times n plus r minus 1 plus n plus r times negative 2 plus 2. You're supposed to take the derivative of all of this. All right? Yes. So you can actually generalize this expression further by having our original assumption that a naught is equal to 1 over here. And then you're basically going to find out a general expression for an, but now it's going to have r's inside of it here. Okay? Ah. Okay. There we go. There's moving. Ah. Yes. Yeah. Yes. Yes. Okay, so we can have an of r is so oh my gosh, the erase. Okay. Yes. Okay, I'm gonna be frank, and I found a mistake on my notes that I did not see earlier. But you basically need to take this whole derivative and you need to make sure that it is the derivative in terms of r. Okay? Not in terms of n. Right? And then once you get this really long, complicated derivative, then you'll get your final expression for Cn, right? Now, at least when I was taking this course, my professor allowed for us to just leave this be. We never actually needed to compute what that final derivative was, because oftentimes it's really, really, really disgusting, right? So hopefully it's the same for y'all. And if not, then I'm so sorry. Yeah, you gotta evaluate it. Um, yes, that is that. Are there any questions? I can imagine that might have been a little bit confusing. So please make sure to ask anything. Okay, yeah. So again, I'm not going to simplify the Cn, but just know the process, right? When we have this full expansion here, you take the derivative in terms of r, and then you're good. All right? Cool. So now, on our very, 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 very last step, we, oh my goodness. We just write down that y is equal to some constant times y1 plus some other constant times y2. Okay. And we know that y1 is just going to be this series right here. 1 over n factorial, big product, negative, oh, sorry. We simplified that further to just be -1 to the n times x to the n plus 2. Okay. And all of this plus c2 times times ln x y1 plus this series right here. Cn evaluated at 1, x to the n plus 1. And this is your final solution right here. Ooh, sorry. Oh, and we also need to multiply the a here. I forgot. Negative ln x y1 plus all that. Oh my goodness. Okay. Very, very, very long question. Are there any questions with that? Yeah, I'd say this is probably like the hardest case Frobenius you could realistically be given on the final. Um, yeah, again, I'm sorry that I can't actually evaluate this derivative. Uh, y'all can feel free to evaluate it if you'd like. It's just I don't have it in my notes and it would take way too long if I tried to figure it out on the spot. So, yes, that is that. Okay. Are there any questions? Okay. Perfect. So, taking up the question that Jiaming put up on the uh on the messages. Just wait, I just need to find it right here. Is this it? Yeah, that is it. Okay. So with the Wronskian, when you're just trying to find U1 and U2 with the variation of parameters and everything, you can often skip out on the work of actually showing the Wronskian and just memorize the system of equations that you need to solve. Okay? So, and I mentioned that just because this whole course is already memorization. Like, it's better to just memorize this one more thing than to potentially get it wrong. So you want to assume if you have a of t y double prime plus b of t y plus y prime plus c of t y is equal to d of t. Okay. And then, yeah, we're going to solve for y. So we have y naught is equal to y1 plus y2. These are our independent solutions for the homogeneous case. Okay. Then we have that our particular solution has to look something like this. Sorry, this should have constants in it. u1 y1 plus u2 y2. Okay. And these u1 and u2 need to satisfy this system of equations right here. u1 prime y1 plus u2 prime y2 is equal to 0. And u1 prime y1 prime plus u2 prime y2 prime is equal to d of t. Okay, this is for d of t is not equal to 0. All right, so these equations are derived directly from the Wronskian. But you could just skip that and memorize that this is what you gotta do. Once you solve these equations, you're good. Right? So I actually have a question planned for this. Okay. So we're gonna go through it together. Right? So we have y double prime plus y prime minus 6y is equal to 52 cosine of 2t. Okay. So this is example number 2. Okay, so this is a non-homogeneous linear second-order differential equation. And so we start off by trying to solve for the homogeneous case. So we have that y double prime plus y prime minus 6y is equal to 0. So as aforementioned, this is, in this case, we can assume that y will be some sort of exponential function. So we need to solve this indicial equation right here. R squared plus r minus 6 is equal to 0. Okay. Then we can factor it out. So we get r minus 2 times r plus 3 is equal to 0. Okay. Then we get r is equal to 2. And we can also get that r2 is equal to negative 3. So we know that y1 would be equal to some constant times e to the 2t. Then y2 is equal to some other constant times e to the negative 3t. But now, moving forward, we have to assume our particular solution yp is equal to u1 y1 plus u2 y2. Okay. And then again, our final solution will be just y equals y naught plus yp. Okay, so to solve for these u1 and u2, we can use these equations right up above. So we have that u1 prime y1 plus u2 prime y2 is equal to 0. So that, oh, that doesn't imply anything. Ah, let me erase. Let me erase. Why would it erase? No. Okay, there we go. And we have that u1 prime y1 prime plus u2 prime y2 prime is equal to 52 cosine 2t. All right. So we can, for our particular solution, it's okay for us to assume that C1 is equal to C2 is equal to 1, right? Because our Wronskian needs to work for absolutely any coefficient that we give it, okay? So with this, we can simplify our computations a lot more, right? So because of that, we get that u1 prime e to the 2t plus u2 prime e to the negative 3t is equal to 0. So that would imply that u1 prime is equal to negative u2 prime e to the negative 5t. Okay, so this is just using um some algebra. Now, if we look up above right here, we know that u1 prime is equal to this expression here. So we can substitute it back into this equation right here. So we get negative u2 prime e to the negative 5t times, sorry. Ah, you can see the eraser come up, but it's still not erasing. Okay, there we go. Times e to the 2t plus u2 prime times e to the negative 3t. Okay. Oh, wait, we also need to take the derivative. Not me forgetting. Yeah, so this is gonna be oh, it's loading. Yeah. 2 2e to the 2t. Then here we have negative 3e to the negative 3t. Okay, cool. So now we can simplify this a little bit further to just get negative 2u2 prime e to the negative 3t minus yeah, minus 3 e to the negative 3t u2 prime. Okay, then this simplifies to just negative 5 u2 prime e to the negative 3t, and we know that this is equal to 52 cos of 2t. Okay, so because of this, we can simplify a little bit further. Okay, let me just double check that all of my working holds. Yeah, e to the negative 3t, e to the negative 3t. Yes, perfect. And so we get our expression for u2 prime, which is equal to negative 52 over 5 cosine 2t e to the negative 3t. Sorry, e to the 3t. No negative. Okay. Then we can take the integral on both sides and solve. Yes, so this is a cyclic integral from 837. The computation is very long, and I still have, yeah, I still have a few more questions that I want to run through. So I won't show all of it, but eventually you'll get that um yes, eventually you'll get your final solution for U2, and then when you solve for U1 prime, we can look back at what we had up here. So we have negative U2 prime e to the negative 5t, okay? And we already have our expression for U2 prime down here, right? So we can actually sub that back in to get negative 52 over 5 cosine 2t e to the 3t times e to the negative 5t. All right. And then we'll get a simplification. Yes. Yeah. Yep. Yeah. Okay. Yeah. So then we get a simplification, 52 over 5 cosine 2t times e to the negative 2t. Okay, that's going to be equal to u1 prime. And then again, we just take our integrals here in terms of dt, and then we get our final answer here. And this particular solution is going to end up looking like this. Sine 2t, yep, minus 5 cosine 2t. Okay, so after you do all of the integration for both of these, ooh, I see something in the chat. What integration is used? Yeah, you have to use by parts twice, and then it's a cyclic integration, so you need to make it like equivalent. Yeah, it's a really gross integral. I could go over it if you want, but yeah, like you do IBP, then you do IBP, and then you'll get some you'll get that your integral I is equal to some linear expression of itself, and then you solve for it. Yeah, it is very long. Yeah, which is why I skipped it. I mean, it's prerequisite knowledge. Hopefully, y'all know how to solve that integral. But yeah, so then for our final answer, we just bring everything together. We get y is equal to y naught plus yp. And then this is equal to C1, scroll up, C1 e to the 2t plus C2 e to the negative 3t plus sine 2t minus 5 cos 2t. And this is your final answer. Okay. So, in general, we have the system of linear equations, okay? Using this system, the system of differential equations, using the system up above, you can get an expression of u1 prime in terms of u2 prime. And then you just substitute that expression back into the second equation, and then you just solve for both of them, right? Okay. Are there any questions with that? Hopefully that makes sense. Okay. So moving on, I'm going to try to do a series solution that is not Frobenius, and then end it off with a non-homogeneous linear, like system of linear ODEs. Okay? So, example number 3. We have series solution. Okay, so we want to solve 1 minus 2x cubed y double prime minus 10x squared y prime minus 8xy equals 0. So we can note that x equals 0 is not a singular point, because if you divided this by that, then yeah, like when you have the limit as x approaches 0 of negative 10x squared divided by 1 minus 2x cubed, that's going to give you a solution. And if you have the limit as x approaches 0 of negative 8x divided by 1 minus 2x cubed, that's also going to give you a solution. So you're good. Okay, so because of that, we can assume that y is equal to the series from n equals 0 to infinity of a n x to the n. Oh, yes. Right. So using this assumption, we can copy it back into this equation right here, 1 minus 2x cubed y double prime minus 10x squared y prime minus 8xy. This is going to be equal to, this implies that y prime is equal to the series from n equals 1 to infinity of a n x to the n plus 1 times n, and that y double prime is equal to the series from n equals 2 to infinity of a n n times n minus 1 times x to the n minus 2. Okay, so we can incorporate all of these back over here. Series n equals 2 to infinity a n n times n minus 1 x to the n minus 2 minus 10x squared series n equals 1 to infinity a n x to the n minus 1 times n minus 8x series n equals 0 to infinity a n x to the n. All right. And then we can expand everything as well to get series from n equals 2 to infinity of a n n n minus 1 x to the n minus 2 minus 2 series n equals 2 to infinity a n n n minus 1 x to the n plus 1, right? Because we're multiplying this x cubed out here, minus 10 series n equals 1 to infinity of n a n x to the n minus 1, sorry, n plus 1, minus 8 series n equals 0 to infinity a n x to the n plus 1. And all of that is equal to 0. Okay. So, because we know all of this is equal to 0, we have to figure out the coefficients for each power of x, right? And we can expect these coefficients to be equal to, we can expect the coefficients to be equal to 0, okay? So, using this equation right over here, we'll see wherever we actually get an x to the 0 expression, okay? So, in this case, that'll only happen once, and it is with this expression right here. So we get 2 times 2 minus 1, a2, which is of course just equal to 2a2, and we assume that that's equal to 0, so we have a2 is equal to 0 here. Okay. Then we look at, for x to the 1, we have a3 times 3 times 2 minus 8a0 is equal to 0. So that would imply that a3 is equal to 4 over 3a0. And then for x squared, we get a4 times 4 times 3 minus 10 times 1a1 minus 8a1 is equal to 0. So that would imply that 12a4 minus 18a1 is equal to 0, which of course implies that a4 is equal to 3 over 2a1. Okay, cool. So now we can come up with a general relationship for every term that is greater than or equal to 2. Okay, so for x to the power of n such that n is greater than or equal to 2, we can substitute we can substitute the expressions up above and change these series so that we're looking at a generalized expression for a n that includes each of these individual series right here. Okay, so that will look like the following. N plus 2 times n plus 1, a n plus 2. So you can notice here we're just substituting in place of n plus 2. That's all we're doing. Okay. And then minus 2, minus 2 times n minus 1, n minus 2, a n minus 1, minus 10 n minus 1, a n minus 1, minus 8 a n minus 1. All of this is going to be equal to 0. Okay. Then we can simplify this whole expression to get n plus 2 times n plus 1, a n plus 2, minus a n times 2n squared minus 2n plus 10n plus 8. Okay. Sorry, this should be an. Of course. It happened again. uh okay, we're back. Oh, oh yeah. There we go. Okay. Sorry about that. So, I need to write down this expression again. So we get n plus 2, n plus 1, a n plus 2, minus 2 n minus 1, n minus 2, a n minus 1, minus 10 n minus 1, a n minus 1, minus 8 a n minus 1 is equal to 0. Okay. And then we have yeah, I'm just gonna skip a few steps right over here. We can adjust this index here by adding 1. So we get n plus 3 times n plus 2 times an plus 3 minus an 2 2 times n plus 2 squared. All of this will be equal to 0. So that is going to imply that an plus 3 is equal to 2an times n plus 2 squared, all divided by n plus 3 times n plus 2, which is of course just 2an n plus 2 divided by n plus 3. Okay, so now we have our relationship between an and an plus 3. Okay. Yeah, right after this, I'll give a short like 10-minute break. Yeah, and then we're gonna go over the system of equations. I'm sorry, it's been like 2 hours straight of talking, but these are long questions. So, we can then say that an is equal to 2an minus 3 times n minus 1 over n. Okay. And then we can figure out our recurrence relations given these original equations that we had up above here. Okay. So since we know that a2 is equal to 0, then that would imply that a5 is equal to 2 times a2 times 4 over 5, which would be 2 times 0 times 4 over 5, which is just 0. Okay. And you can see that this relationship will keep going. And it'll keep going for every a3k plus 2. It'll be equal to 0 for all k in the natural numbers. Then, since we know that a3 is equal to, yeah, 2a naught times 2 over 3. Okay. Then we know that a6 is equal to 2a3 times 5 over 6. Okay. Then we know, yeah, 2a3 times 5 over 6, which is equal to 2 squared a naught, sorry, yes, a naught, yeah, times 5 over 6 times 2 over 3. And then you keep going until you find a relationship that you're confident in. So this will be 2a6 times 8 over 9, which would be 2 cubed, 2 over 3, 5 over 6, 8 over 9, a naught. Okay. And so, for this relationship right here, we can say that every multiple of 3, sorry, not that one. Okay, it won't let me erase. Cool. Every multiple of 3 is going to have the expression 2 to the k, right? It's raised to the power of 3 right there, times the big product from m equals 1 to k of 3m minus 1 divided by 3m a naught. Whew. Okay. You can see this is going to work out with everything I've calculated up above. So now for the very last relation we need to look at, we have a4 is equal to 2a1 3 over 4. We have A7 is equal to 2 times A4 times 6 over 7, which is equal to 2 squared. 3 over 4, 6 over 7, A1? Yes, A1, not A naught. There we go. A1. Okay. And so we can say that A3K plus 1 is equal to 2 to the K times some 3 times 6 times 9 times dot 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 times 3K divided by 4 times 7 times dot 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 times 3K plus 1, A1, which of course we could just generalize using our product notation. M equals 1 to K of 3M divided by 3M plus 1, A1. Oh, okay. So, since this is the case, well, okay, there we go. Since this is the case, now we've come up with all of the recurrence relations here for absolutely any possible member of the sequence. So we know that y is equal to the series from n equals 0 to infinity of an x to the n, which will be equal to a naught times 1 plus, we add this one so that we have a naught included in our expression, plus the series from k equals 1 of 2 to the k, big product, m equals 1 to k of 3m minus 1 divided by 3m times x to the 3k. So this is looking at our first relationship right here. All right. Then we add a1 times x, again, so that we can include this a1 term here, plus the series from k equals 1 to infinity of 2 to the k times the big product from n equals 1 to k of 3m over 3m plus 1 times x to the 3k plus 1. All right. Yes, this is our generalized solution. Now, one other thing that these questions might ask you to solve for is the radius of convergence for these solutions here. Okay. So if that's the case, you will have to use the ratio test. So for radius of convergence, then we have the limit as k approaches infinity of, you take each of these individual relations, okay? And then you check the radius of convergence for both of these series here. So we have a3k plus 1 times x to the 3k plus 1 divided by a3k x to the 3k. This will be equal to the limit as k approaches infinity of, since we're using this first relationship here, just up above, it will be 2 to the k plus 1 times 2 times 5 times dot 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 times 3k plus 2 divided by 2 to the, sorry. Oh, it should be Yeah. Wait. Oh, no. This is right. Yes. Yes, this is right. 2 to the k plus 1, and then divided by 2 to the k times 3 times 6 times dot 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 times 3k plus 3. Okay. And then all of this will be multiplied by, oh, wait, there's yet another expression up above. Sorry. Well, erase. There we go. There we go. Erase. Okay, cool. Yes, I forgot that the numerator is also multiplied by this expression here. Times dot 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 times 3k. Uh, yes. Yes, and then we have times x cubed up above there. Then we also, yeah, and then we also have yet another division for 2 times 5 times dot 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 times 3k minus 1 down below. Okay. So, continuing our ratio test, we have the limit as k approaches infinity of 2 up above times 3k plus 2 divided by 3k plus 3 times x cubed, which is equal to 2 times x cubed. We, of course, want this expression to be bounded above by 1 for the ratio test to be successful. And so we get that our radius of convergence is bounded above by 1 over the cube root of 2. Okay. So we can set this to be equal to rho 1. Then we also need to check the radius of convergence for this series right here. Okay. And so we take the limit as k approaches infinity of a uh of a 3k plus 1 plus 1 times x okay, times x to the 3 times k plus 1 divided by a 3k plus 1 times x to the 3k plus 1. And spoiler alert, this is going to end up looking very, very, very similar to the expression that we had up here. It'll simplify to just be 2 times x cubed times the limit as k approaches infinity of 3k plus 3 divided by 3k plus 4, which will be equal to 2x cubed, which is bounded above by 1, which would be equal to, which would imply that absolute x is bounded above by 1 over the cube root of 2, which is equal to rho 2. So, in this scenario, we take our radius of convergence to just be rho to be equal to the minimum between rho 1 and rho 2, which in this case, they're luckily equivalent. So we can just do 1 over the cube root of 2. And this, all of this together is our final answer. Okay, I'm gonna have y'all take a quick 10-minute break. Then when you come back, I'm gonna do one system of differential equations question, and then it'll be a quick Q&A session. So yeah, see you in 10 minutes. Right. Hello. We are back. Okay. So this was the long series solutions question. Now I'm going to move on to a system of linear ODEs question. Okay. So when we have example number 4, system of linear ODEs. Okay. So let's say we have this expression right here. X prime is equal to -6, 4, -1, -2, x plus e to the -3t, 2e to the -4t. Okay. So this is a non-homogeneous system of linear ODEs. So we can so we can solve it using a very, very, very similar system as what we did before with those with the other non-homogeneous linear equations. Okay, so if we have we know for sure that our matrix transformation looks like this. Okay, and we need to figure out the eigenvalues for A, right? Because we know that our final solution y will be equal to C1 C1 e to the lambda 1 t v1 plus C2 e to the lambda 2 t v2. Okay. And lambda 1 and lambda 2 are eigenvalues. So we have to take the, it's just loading. Okay. We have to take the determinant of A, which is, oh, sorry. The determinant of, erase. There we go. The determinant of A minus I lambda. Okay. This will be equal to -6 minus lambda times -2 minus lambda plus 4, which will be equal to 0. Okay. So that would imply that lambda squared plus 8 lambda plus 16, which is equal to lambda plus 4 squared, is equal to 0. And so we have that lambda 1 is equal to lambda 2, which is equal to -4. Okay. So here, and it closed again. I'm so sorry this keeps happening. I don't know why it does. I'm pretty sure it's the program just crashing. OneNote. There we go. Okay, and of course oh yeah, okay, it actually saved a lot. That's good. All right. Sure. Cool. Okay. Zoom in. All right. So we have the determinant of A minus I lambda, which we computed to just be lambda plus 4 squared, which is equal to 0. So then that would imply that lambda 1 is equal to lambda 2 is equal to -4. So because we have equal roots, this solution is actually going to look a little bit different. Okay. So it will not look exactly like this. It will look like y equals c1 e to the, let's set this to be equal to lambda. Yeah, e to the lambda t times the corresponding eigenvector plus c2 t e to the lambda t times the same vector plus e to the lambda t times some other vector. Okay, and this vector eta is a vector such that a minus lambda I times this vector is equal to the eigenvector. Okay, so then this is not the case we're looking at here. We have to look at this case right over here because we have equal roots, right? Are there any questions with that? Cool. So we have yeah, so we have this information right here. And so now we need to compute the eigenvectors. Okay. So we have -6 minus 4, sorry, -6 plus 4, 4, -1, -2, plus 4. This is equal to -2, 4, -1, 2. Using row operations, we get this general matrix right here. And then this simplifies to 1, -2, 0, 0. Okay. So therefore, we know that x minus 2y is equal to 0. So that would imply that xy is equal to 2, 1, y. Therefore, our first eigenvector will be equal to 2, 1. And so if we want to figure out this eta vector right here, we look at a minus lambda I times this vector is equal to, and of course it closes again, one note. Okay, very cool. Share screen, this, share. All right. I'm just gonna very quickly write down what I had before. Yeah, so for eigenvector, we have -2, 4, -1, 2, 1, -2, 1, -2, 1, -2, 0, 0. So therefore, x is equal to 2y, implying xy is equal to 2, 1, y. And so our eigenvector is equal to 2, 1. Okay. So now for our second vector that we're going to include in this solution, we have to solve, if one note will load, yeah, a minus lambda I times this vector is equal to our eigenvector. Okay, so therefore, we look at this matrix over here. So we have -2, 4, -1, 2 times some unknown variables. So we go like, we could just use eta 1. eta 2, okay, to be equal to 2, 1. So for this to be the case, we would need, it's not letting me scroll down. Just wait, technical difficulties. Okay, we're good. Oh, okay. Yeah. Okay. Yes. Like that. So now we have this system of linear equations. We have negative 2 eta 1 plus yeah. Yeah. Plus 4, sorry, not y, plus 4. Okay, I'm just gonna scheme it into being an eta 2 is equal to 2. And then we have negative eta 1 plus 2 eta is equal to 1. Okay, eta 2. So we can just choose literally anything that will work here. In this case, you can notice that if we chose eta 1 to be equal to negative 1, and then if we chose eta 2 to be equal to 0, then this solves the system, right? We have negative 2 times negative 1 is equal to 2, and negative 1 times negative 1 is equal to 1. So we're good. And so, therefore, eta is equal to negative 1, 0. Are there any questions with any of this? With the equal roots solution? Okay. And so our general solution, okay, our general solution for our homogeneous system will be C1 times e to the 4t to the negative 4t times 2, 1 plus C2 times t e to the negative 4t times 2, 1 plus e to the negative 4t times negative 1, 0. Okay. So this is our general solution for a homogeneous case. But we know that this is a non-homogeneous equation because of what we have right over here. Okay? So therefore, we need to do a little bit more work until we get our final solution. So just like before, we guess that our particular solution will be equal to u1 e to the negative 4t 2, 1 plus u2 t e to the negative 4t 2, 1 plus e to the negative 4t negative 1, 0. Okay. And just like before, we have that u1 prime times e to the negative 4t to 1 plus u2 prime times t e to the negative 4t to 1 plus e to the negative 4t negative 1, 0 is equal to what our non-homogeneous extra fluff is. So it would be e to the negative 3t and then 2e to the negative 4t. Okay. Yeah. Again, it's from what we had up here. Just one moment. Okay. Why is it doing this? What's happening? Oh no. Okay. All right. Yeah. So then once we have this, we could get two different equations looking at all of the expressions in our first entry of the vector and looking at all of the expressions in the bottom entry of the vector. Okay. So then therefore, we have that e to the negative 4t times 2u1 prime plus 2t minus 1 u2 prime is equal to e to the negative 3t. And we get that oh, actually with this information we can get our general solution for oh, okay, wait. Never mind. Yeah. Sorry. Yes, we get this first expression here. Then we also get e to the negative 4t times u1 prime plus t u2 prime, that this is equal to 2e to the negative 4t. So then that cancels out nicely, and we get u1 prime plus t u2 prime is equal to 2. Nice. So with these two expressions right here, okay, we can get a simplified expression isolating for u2 prime. So we can have this expression right here. I'm going to just label this with a star. If we work on the star, we have 2u1 prime plus 2t minus 1 u2 prime is equal to e to the t. Okay. And so if we use this equation right here and we subtract by 2u1 prime minus 2t u2 prime, which is equal to -4, then we get our u1 primes will cancel out. This part of the u2 prime will cancel out. So we're only left with negative u2 prime is equal to e to the t minus 4. So that implies that u2 prime is equal to 4 minus e to the t. And then we can take the integral on both sides to get that u2 has to be equal to 4t minus e to the t. Okay. So now we have our expression for u2, and we can substitute back into this equation up above to get our expression for u1 prime. Okay. So we have u1 prime plus t times 4t minus e to the t is equal to 2. And so that would imply that u1 prime is equal to 2 minus 4t. Oh, this should not have a t in it. Plus plus t e to the t. Then again, we take the integral on both sides. And then we get u1 is equal to 2t minus 2t squared plus OneNote is loading. Okay, plus t e to the t minus e to the t. Okay. And so, with all of this, we get that our particular solution is equal to um is equal to yeah, it's equal to this long expression for u1. So it's not letting me write again. Yeah. Okay, wait. Yeah, it's okay, it's okay. There's only a little bit longer. Yeah, so it'll be 2t minus 2t squared plus t e to the t minus e to the t times e to the negative 4t to 1 plus 4t minus e to the t times y2. So t e to the minus 4t to 1 plus e to the minus 4t negative 1, 0. And our final solution will be just x naught plus xp, which will be this really, really, really long final expression. The c2 t e to the negative 4t to 1 plus e to the negative 4t negative 1, 0 plus that expression that I just wrote up above. Minus t squared plus t e to the t minus e to the t e to the minus 4t to 1 plus 4t minus e to the t e to the minus 4t to 1 plus e to the minus 4t negative 1, 0. And that's that. That is your final solution. Oh, okay. Just in time. So for the next 20 minutes, I will allow for anyone to ask any questions they want. If you want me to look over specific types of questions and stuff, you can also request it. I have a backlog of questions here, like ready for people to do. But yeah. So yes, you can leave your questions in the chat. And if not, I'll just go over more stuff once OneNote starts responding. Okay, we've pivoted to the Zoom whiteboard. But yeah, if anyone has any questions, leave them in the chat. And if not, then yeah. Radius of convergence. Okay. Do you want me to go over what I did before with radius of convergence again, like more slowly, or do you want me to just go over how to solve radius of convergence in general. Okay. So when we have our final solution, y is equal to the series from n equals 0 to infinity of an x to the n. Our radius of convergence is the values from x, like, because this is the Taylor expansion from when x is equal to 0. Okay? And so, yeah, our radius of convergence is the points that will actually end up converging to something finite before our power series just blows up, right? So then we can figure out our radius of convergence like that, right? So in general, for radius of convergence, there are two tests that we look at, okay? You can either look at the limit as n approaches, the limit as k approaches infinity of the absolute value between ak plus 1 divided by ak, okay? And then this is going to be multiplied by x right here, right? And so long as this ratio is less than 1, we know that this series will converge for those values of x. Okay, so for example, if uh if your limit as k approaches infinity of ak plus 1 over ak is equal to 8, then your radius of convergence would be 1 over 8 up above, right over there. Okay. Yes. Yeah. The issue, oh, I forgot I'm not in OneNote anymore. The issue with when we're working with these differential equations is that, oh, just let me draw. What? Okay, cool. Yeah, the issue is that when we're working with these differential equations, is that oftentimes our recurrence relations will only work for specific um modular powers, right? So for example, like you might have an expression for a3k plus 1 or a3k or for a3k plus 2, right? And then you'll have something like y is equal to the series from k equals 0 to infinity of um some a3k times x to the 3k plus some other series a3k plus 1 x to the 3k plus 1 plus some other series k equals 0 to infinity a3k plus 2 x to the 3k plus 2. Okay, so when your solution looks like this, you have to go through it with a little bit more care, right? So you go through this exact same process, but for each of these series individually, right? So you would have the limit as k approaches 0 of a3 times k plus 1 divided by a3k, and then up above we have x to the 3 times k plus 1 divided by x to the 3k. And then now this expression simplifies to look like this. So this is our ratio test that corresponds with this series right here. And so when we get these radii of convergence, you might have this be equal to like rho x cubed, and that's less than 1. So that would imply um absolute x is less than 1 over the cube root of rho. Okay? And so you won't be able to just say concretely that this is your final radius of convergence, because you want to make sure that each of these individual series converge. So you would compute the radius of convergence for this series and for this series, and then you would get that your x is bounded above by the minimum between the first radius of convergence, the second radius of convergence, and the third radius of convergence. Okay. And of course, this can be generalized to like any combination of series that we have here. It doesn't just need to be 3. Then you would just be taking the minimum of even more radii of convergence. But yeah, does that make sense? Does that make sense? Was that helpful? Awesome. Okay, are there any other questions? All right. Well, yeah, I'm not too sure that there's enough time to go over another question. As y'all can see, we only got through like 5 questions the whole time. Ugh. These B44 these B44 questions are so long. But yeah. Uh so yes. If there are no more questions, then we might end a little bit early. 10 minutes early. Yeah. Speak now or forever hold your peace. Cool. um yeah. David, do you have any questions? Awesome. Okay. Best of luck on your final, and thank you so much for coming. Of course, of course. And